lecture is based on the basics of projection. And I first want to go over coordinates. So coordinates can be expressed in many forms, but the most basic forms where we express coordinates are based on latitude and longitude coordinates. So here for Glendale Community College, our coordinates are 34.16689 degrees north, and our longitude is 118 degrees, 0.22834 degrees west. So we have our coordinates in decimal degrees, but also we could have our coordinates in degrees, minutes, and seconds format. So for Angelina Jolie, we could see here on her arm, she does have specific coordinates based on the format of degrees, minutes, and seconds. So here we could see 43 degrees, 41 minutes, and 21 seconds north. So later in lecture, we're going to go over how you could convert between decimal degrees to degrees, minutes, and seconds format. I want to go over the importance of coordinate systems and map projections. So again, coordinate systems, like we just went over, latitude and longitude, and map projections are the building blocks of your GIS or any kind of spatial data. So here we have an example of there being many different types of maps of South America, and these are map projections, and they're color coded to the specific projection. So we could say with green, it's the Mercator projection, and we have an oval projection. So what I do want you to notice here is that I do want to use the drawing tool. Let's see. I do want you to notice that based on the different types of projections, you will have a different endpoint. So the endpoint for South America here is different from the endpoint of this projection that's displaying South America. So it's very important that, especially when we have been making maps, that all of your data layers are in the same type of projection, especially when you use the ArcGIS Pro software. That one you will have to change the projections to be the same, because if you use two different layers with two different projections, they will not overlay correctly, just like we see in these examples. So the World Map Mercator's projection, this is a commonly used projection for displaying the world map. And we could see that these continents or the size of these countries are distorted. For example, we have Greenland here, and Greenland is about the size or even larger than Africa. Also, we could see with the United States that it is half of Africa. So again, the size is distorted here. And I do want to mention Africa's actual size. And here we could see this is the true size of Africa. And we could see that United States fits in the small corner part of Africa, and we could see that it fits many other different countries such as China and so on. So here in this type of Mercator's projection, it's making Africa, the size of Africa, small, whereas this is the actual size. So again, next week we'll talk more about projections, but just keep that in mind that these different projections matter. So again, we need to convert the Earth Earth's three-dimensional surface to a flat surface. So 3D means three-dimensional, so the Earth is round, and we need to convert it to a flat surface. So a flat surface, such as, our computer screen is a flat surface, a flat map. So in order to do that, we need to define the shape of the Earth. There are different ways to define it. There are spheroids, ellipsoids, and geoids. And next we're going to talk about datums, and we'll cover projections next week in lecture. So again, we're looking at the sphere, ellipsoids, and datums are connected to a specific ellipsoid, and lastly, a geoid. So here for Earth's shape, a sphere, you could see that this black outline here is representing a sphere. And a sphere is good to use for geographic coordinates such as latitude and longitude, and also it can be used for small scale maps. An ellipsoid is a more accurate representation of Earth. We can see that with an ellipsoid, it's this green oval shaped outline. An ellipsoid comes from the word ellipse. Ellipse is an oval shape. So again, we could see that it's flat at the poles and it extends, or it's wide at the equator. And that's an ellipsoid. So and then later in lecture, we're going to talk about what makes an ellipsoid the way it does. And a geoid is this colorful Earth representation, and a geoid is good for surveying, such as when you're using the compass, and also for very complex mathematical equations. So again, we're going to learn that a geoid is based on the gravitational pull on Earth, of the Earth. But before we dive into those three different topics, I do want to stress the importance of measuring the spherical Earth. So again, we have latitude, also known as parallels, and latitudes extend from the equator at 0 degrees to either 90 degrees north in the northern hemisphere or 90 degrees south in the southern hemisphere. And the same applies for longitude coordinates. So for longitude, it's also known as meridians. Our 0 degree longitude line is called the prime meridian, and our maximum degree is 180 degrees, and it's called the international date line. So your coordinates are either going to be in the eastern or western hemisphere. Here we have a diagram of the maps of the Earth based on longitude and latitude coordinates. Again, longitude and latitude coordinates are angular measurements from the center of the Earth. So from the center of the Earth, this is extended outwards to 60 degrees east and 55 degrees north latitude. And we can see here the equator all the way extending to the North Pole and South Pole. And for your longitude lines, again, we have the prime meridian here, and then our western hemisphere on this side, on the left side, and our eastern hemisphere on the right side. And again, when you plot it together, you're going to reference your latitude coordinates first and then your longitude coordinates second. So here, for example, we have 30 degrees north latitude and 60 degrees west. So this line is 30 degrees north and this line is 60 degrees west. Also, you can express latitudes either in positive or negative signs, and the same for longitude. So we could see that in the southern hemisphere, it's expressed as a negative sign, whereas in the northern hemisphere, it's expressed as positive. And then if we're looking at our longitudes, in the western hemisphere, it's designated as negative, whereas in the eastern hemisphere, it's designated as positive. Also, we have our international date line, and the reason this line is so specific is because the small islands wanted to be included on the eastern hemisphere of the international date line. So again, like I said in the beginning of lecture, you could express latitude and longitude in degrees, minutes, and seconds. So here's an example of Sierra Hall, a building in Northridge. And this specific building in Northridge, the coordinates are 34 degrees, 14 minutes, and 18 seconds north, which is our latitude, and then 118 degrees, 31 minutes, and 51 seconds west. You could also express it with a negative sign. So again, we know the northern hemisphere was a positive. So if it's positive, you just leave it alone. But if it's negative, you will put the negative in front. So the negative sign applied only to the western hemisphere, which this is west, as well as the southern hemisphere. Also, you can convert degrees, minutes, and seconds to decimal degrees. So again, using the same example of the latitude here for Sierra Hall, for the Sierra Hall building, you're going to keep your 34 degrees, and your 34 degrees, you're going to put it in front of the decimal point here, and then you're going to divide your minutes with 60 and your seconds with 3,600. Like we see here, 14 divided by 60 and 18 divided by 3,600. So when you sum this up, this is the sum 2983 degrees. So that is how you convert degrees, minutes, and seconds to decimal degrees. So now let's talk about the Earth's shape, such as the ellipsoids, the geoid, as well as datums. So again, an ellipsoid, also you can call it a spheroid, is a sphere that is flattened at the poles, like we see here, and it's wide at the equator. So there are examples of ellipsoids. We have the WGS 84 and the GRS 80. So here is an ellipsoid, and this is an ellipsoidal model of the Earth's shape. So again, it's flattened at the poles and it extends at the equator. So we have the semi-major axis, which is the longer axis, and we have the semi-minor axis, which is the shorter axis. So again, this is an ellipse, and an ellipse is an oval shape with a major axis, which is our long axis, and our short axis. And when you rotate the ellipse, the shape of the rotated figure is the ellipsoid. So again, the reason why the A here is the longer axis is because when the Earth spins on its axis, The centripetal force makes it bulge at the equator, so that's why it has a longer axis near the equator than at the poles. And we're going to learn that we need to find an ellipsoid that fits the surface of the Earth, which is our geoid. So there are many different types of ellipsoids because it needs to match the surface of the geoid. So the geoid is defined as the surface of the Earth's gravity field. So it's a model of global mean sea level that is used to measure precise surface elevations. So again, we're looking at the gravitational pull of Earth. So the geoid represents a surface where all of the pull of gravity is the same. So again, if we were to remove these continents or land masses, what would the mean sea level be there? And you could also think of it as cutting a canal through Africa and seeing how would the water rise. And we could also look at the oceans. We could see the ocean surface can either go up or down. Here we can see that it's decreased, and here it looks like we could see that it bulges up. So again, this is based on the density of rocks or other features that influence how strong the pull of gravity is at any potential location. So again, we're looking at the strength of the pull of gravity and where water would pool. So if there is a higher gravitational pull, like we see here in this area, that means there would be more water pooling or piling up. So again, for a geoid, we're looking at the average mean sea level. And since the mass of the Earth is not uniform at all points, like we could see here, the direction of gravity changes and the shape of the geoid is irregular. So what is the need of different ellipsoids? Well, we could see here in this example, there are 3 different ellipsoids that are being shown here. So if you're looking at the North American region, part of the geoid, we would say that the North American ellipsoid, which is Clark 1866, best fits the North American region here. And then we could say for Ireland, the Irish ellipsoid that has been modified best fits this geographic region. So you could think of this uneven surface as the mean, as the geoid, and which ellipsoid would best fit for this geoid. And again, the best fitting global ellipsoid, this is based on global, the origin of the global ellipsoid, it's based on the Earth's center of the mass. So again, this is the best fit globally, whereas the North American ellipsoid is more concentrated to the North American region. So again, an ellipse here, we could see that for the major axis, it's 6,378 kilometers, whereas the minor axis B is 6,357. So the equator axis is longer than the pole axis. So when you rotate an ellipse around its axis, it becomes an ellipsoid. So there are many different types of ellipsoids. I just went over an example of using a North American ellipsoid known as Clark 1866, and it's a perfect fit for North America. Or again, you could use a global ellipsoid that's more focused. The origin is at the center of the Earth. So one particular spheroid is distinguished from another by the lengths of the semi-major and the semi-minor axis, like we see here. So again, we could see that the semi-major axis is different in Clark 1866 compared to GRS 80. So 6,378,206 is the B is the equatorial axis. And for the GRS 80 spheroid or ellipsoid, again, it's used interchangeably. It's 6,378,137. And then we could see with this ellipsoid, it's similar to the GRS 1980. And the reason for that is because this is a global referenced ellipsoid. So again, what I just explained, the best fitting global ellipsoid is best for the globe, and you could have a local reference ellipsoid based on your geographic region. So there has been many spheroids or ellipsoids that have been devised, like we can see here. Many different countries use their own type of ellipsoid. We could see WGS 84, GRS 80, and WGS 72. These are internationally recognized ellipsoids. And the reason for that is because it's based on the center of Earth's mass. Okay, so this will fit the geoid. It's a better fit for the geoid. So now we're going to talk about datums. And again, these are three different ellipsoids. We could see a blue ellipsoid as number 1, the second ellipsoid as the red ellipsoid, and then the green ellipsoid could be number 3. And you could think of this yellow being the geoid. So again, the geoid takes into account the average mean sea level based on Earth's gravitational pull. So we could see here that for number 1 ellipsoid, this is a best fit for this geographic region here for number 1. But it's not a best fit for the geographic region here because this ellipsoid does not match perfectly with the geoid. Whereas ellipsoid number 2 perfectly matches this part of the geoid. So if you lived in this location here and you wanted to map out this location, you would want to use this ellipsoid, ellipsoid number 2. Whereas ellipsoid number 3, you wouldn't want to use ellipsoid number 3 if you were located here. It looks like ellipsoid number 3 touches the geoid perfectly here in this area. So again, you could see that the origin of these different ellipsoids are off. They're not placed exactly on top of each other. So ellipsoids can be different shapes and it could have a different origin. So one datum I want to mention is the NAD 1927 datum. So datums are tied to ellipsoids. But before I get into that, surveyors inserted brass monuments into Earth known as survey benchmarks. So this is an example of a survey benchmark for NAD 1927. This is a reference point. And again, surveyors measured extremely precise locations on the Earth's surface using latitude and longitude coordinates. So again, NAD 1927 is a horizontal datum, and NAD 1927 is a model that translates an ellipsoid into latitude and longitude coordinates. So the NAD 1927 datum is based on, we just reviewed it right now, the 1866 Clark ellipsoid. So again, NAD 27 put a fixed latitude and longitude position at Meads Ranch, Kansas. So we could see Meads Ranch, Kansas here. And the specific latitude and longitude coordinates for this benchmark is 39 degrees, 13 minutes, and 26.686 seconds north. And for longitude, it is 98 degrees, 32 minutes, and 30 seconds west. And the reason they chose this area, this point here, as the reference point for NAD 1927 is because it was near the center of the contiguous United States. So all the points in North America use the Meads Ranch as the reference point to give the location and direction away from Meads Ranch. But the NAD 1927 is retired due to it being inaccurate latitude and longitude coordinates. So now we use the NAD 83 datum. So now we use the NAD 83 datum. And according to NOAA, the geographic coordinates in NAD 27 datum might be hundreds of meters different from a NAD 83 datum. So again, a datum is an estimate of the ellipsoid. A datum is built on top of the selected spheroid and can incorporate local variations in elevation. So a datum is attached to a spheroid or an ellipsoid. Like we just went over the ellipsoids, and we know that different ellipsoids have different major and minor axes. So you want to choose the ellipsoid that best fits your region. So again, an estimate of the ellipsoid allows the calculation of the elevation of every point on Earth, including sea level, and this is called a datum. Examples of datums for the US include NAD 27, like I just went over. Here's the reference point for NAD 1927 at Meads Ranch, Kansas, and NAD 83. So NAD 83 is more accurate for the geographic coordinates compared to NAD 27. And international datums include WGS 84. So here again, we went over an ellipsoid. An ellipsoid is an oval shape. We know the major and minor axis. The major axis is longer than the minor axis. We also have, so the ellipsoid is this dashed line here. That's the ellipsoid. The geoid, again, it's based on the average mean sea level from Earth's gravitational pull. So that's this irregular blob we see here. And we have the local datum, NAD27. So we could see the local datum, the origin is off-centered. And we definitely know it's off-centered because we know with the NAD27 datum, it referenced the origin in Kansas City. So, whereas the WGS 84 is an Earth-centered datum. This is located in the center of the Earth's mass. And to find the center of the Earth's mass, they used satellites to make sure it's really specific. So again, the Earth-centered datum is more accurate to use for the whole globe. So here we could look at a local datum. Again, this local datum is attached to a local referenced ellipsoid. So the spheroid touches the edges of the Earth right here. So it's a good fit here, but it's a bad fit here. So if you wanted to study an area here, you would choose a different datum. You wouldn't choose a local datum like NAD27, for example. What you would want to use is a Earth-centered datum. And again, this is an Earth-centered datum like WGS 84 or NAD 1983. This is the best fit for the entire planet.